Welcome to my video on 9-3 geometric sequences. So in this lesson, basically we're going to do everything we did in the prior lesson with arithmetic sequences and apply it to geometric sequences, which are the result of multiplying the same number over and over and over again. So as I do now, just to kind of review what we do already know, it asks to find the next three terms of the sequence 81, 27, 9, and 3. Write a recursive formula for that sequence, and then to define it as an arithmetic or geometric sequence. So if we take a look at this particular set of numbers, we're going from 81 to 27 to 9 to 3, and we're assuming that that is continuing because of the dot, dot, dot. Now, to get from 81 to 27, we are dividing by 3. So what you want to do is, if you recognize that pattern, you have to check between every number. Am I also dividing by 3 here? And the answer is yes. Am I also dividing by 3 here? And the answer is yes. So that means to get to the next 3 terms, we're going to continue dividing by 3, right? So 3 divided by 3 gives me 1. So that means the next term of my sequence should be 1. Then we take 1 and divide it by 3. Now we're going to leave things as a fraction in its most reduced format, not its decimal equivalent. So we can go directly into 1/3 as our next term of the sequence. And now we have to take 1/3 and divide it by 3. Now, the thing to remember here is that dividing by 3 is the same as multiplying by 1/3, okay? And I want you to keep that idea in your mind because that's going to be important when it comes to the recursive formula. So if I'm multiplying by 1/3, remember we multiply across the top, then across the bottom, and we see that our next term would be 1/9. All right, making the next 3 terms of the sequence 1, 1/3, and 1/9. So now, can we create a recursive formula for this particular sequence based off what we see? Well, remember, a recursive formula is like that building block formula. You have 2 parts. You have your initial condition, which is your A1 term, right? You have to define that. And then you have your rule. And that rule always is built off the term before it. So as a recursive formula, our initial condition, or A sub 1, is going to be our first term. So in this case, that would be 81. Now to find the following terms after this, A sub n, what we are doing is we are going to be multiplying A sub n minus 1, or the term before it, by 1/3. And I like to represent this as multiplying by 1/3 as opposed to dividing by 3. So that way when we talk about what is called our common ratio, which is what we'll talk in detail about today, it will have to be represented as a fraction as opposed to a division question. Okay? So now, is this arithmetic or is this geometric? Well, the main difference between an arithmetic and geometric sequence is that an arithmetic sequence is the result of adding or subtracting the same number over and over and over again, whereas a geometric sequence is the result of multiplying or dividing by the same number over and over and over again, making this particular sequence a geometric sequence because we are multiplying by 1/3 repeatedly, or if you like to think of it another way, dividing by 3 repeatedly. Okay, so what else do we need to know about geometric sequences? Well, we need to be able to identify situations in which geometric sequences come about. Now, if we remember from the prior lesson, when we had arithmetic sequences, typically the numbers were generated in a linear fashion, right? We were adding the same amount, which resulted in almost like a slope for each particular term to get from one to the other. Whereas geometric, because we are multiplying by the same number over and over again, is going to resemble our exponential models. Okay, so if we read these 4 situations, one of them can be modeled using a geometric sequence, where the other ones are going to be more so arithmetic. So a cell phone company charges $30 per month for 2 gigabytes of data and $12.50 for each additional gigabyte of data. So how is the price changing? Well, we are adding the same amount, in this case $12.50, every time we have an additional gigabyte. So the fact that it's adding by the exact same amount repeatedly tells me that if we were going to model this as a sequence, it would be arithmetic. Okay, so that's the indicator there. That would be modeled in a linear fashion. Choice B, the temperature in your car is 79 degrees. You lower the temperature of your air conditioning by 2 degrees every 3 minutes in order to find a comfortable temperature. So again, how are the values changing? Well, they're changing by the same amount every time. We are lowering, which means subtracting, by 2 degrees every 3 minutes. So again, because we are repeatedly subtracting, that's going to be similar to a linear model, making this one arithmetic as well. Now we take a look at choice C. David's parents have set a limit of 50 minutes per week that he may play online games during the school year. However, they will increase his time by 5% per week for the next 10 weeks. So a key indicator here is this 5%, right? Think of it that way. 5% will not always be the exact same value every week, okay? 5% of your time this week will be different from the 5% of your time next week, different from the 5% of your time the week after that. So in order to calculate that, right, we are using multiplication, right, to find our percentage values, making this one a possible geometric sequence, because that percentage implies we will be multiplying. And choice D says, Sarah has $100 in her piggy bank and saves an additional $15 each week. Again, a constant change per week. Add, 15, 15, 15, making this one arithmetic. Okay, so now we see the wording on real-world context type questions for what could potentially be modeled as arithmetic versus potentially modeled as geometric. Okay, so we first need a formula to help us with our geometric sequences, and then we will be focusing on how to apply these formulas to some word problems for the day. So the explicit formula for geometric sequences can be modeled by the following. A sub n, meaning any nth term, is equal to a sub 1, which is our initial term, our first term, times r, which, if we remember from the vocabulary the other day, is called our common ratio, raised to the n minus 1 power. Now, looking at this formula, right, it's very similar to our exponential equations, right? We have a base raised to a power. We are multiplying it by our initial condition, right? And so our geometric sequences are going to take a exponential type of change between terms. Now, it's not going to be exactly like an exponential function. There's a few differences, but at least we can see how the growth can occur for these types of formulas. Okay. Now, again, the common ratio, this is the reason why I represent division with fraction, multiplying by a fraction, is because that common ratio you can't represent as a division. It must be represented as, multiplying by a fraction every time. So write an explicit formula for the following sequence. Use the formula to find the eighth term of our sequence. So now we have the benefit that today everything we talk about will be geometric, meaning anytime we see explicit formula, we need to understand that we're going to be using a sub n is equal to a1 times r n minus 1. Now, of course, on your tests and on Regencies, all the sequences will be mixed up. So it's important to know that we are using this formula because the change from here to here and here to here is a result of multiplying by the same value over and over again. So in this case, going from -3 to 6 and then 6 to negative 12 is the result of multiplying by a -2, right? Because that's the only way to switch back and forth between negatives and positives, right? So if I multiply 6 by -2, we also see that we get -12, making our common ratio, or our base of our exponent, a -2, which is different from exponential functions, which we've restricted our bases to be positive values, okay? So that's one difference we will see, okay? So now let me plug in my values. A sub n, any nth term, is equal to my initial term, which in this case is -3, times my common ratio of -2 raised to the n minus 1 power. Okay, so that right there is my explicit formula, and I can use this formula to find the 8th term by substituting 8 in for my n. So a sub 8 means my 8th term is equal to -3 times -2 to the 8 minus 1 power. So here we can plug this into our calculators, raised to the 8 minus 1 power, and we get that our 8th term should be 384. Okay, and if I continue the pattern of multiplying by 2, I should get 384 again. So let's take a look at some other questions. So here we have, suppose a balloon is filled with 5,000 centimeters cubed of helium. Now, if you were in class, this would be a GIF and it would be a deflating balloon. But that's besides the point. It then loses 1/4 of its helium each day. How much helium will be left in the balloon at the start of the 10th day? Okay, so we have a balloon. It's losing air. Think more like the foil balloons, right? The ones that kind of hang around your house for a really long time. These balloons lose 1/4 of its helium per day, meaning it's not losing all of its helium all at once, okay? So, how can we write a sequence of numbers to represent this situation? Well, let's think about losing 1/4 of your helium per day. If I multiply 5,000 by 1/4, right, which is really like dividing by 4, I get 1250. But that's not the amount of helium left in my balloon, which is what I'm asking about in this question. So I would have to take 5,000 and subtract 1250 to actually get that amount, which would be 3750. So I want you to think back to our exponential models. When we talk about loss, right, we represented these as a decay model, meaning a fraction in between 0 and 1 to represent loss of, in this case, helium. So if we are losing 1/4 of the helium per day, it's like we're taking 1 and subtracting 1/4 of it, making my new base really 3/4. So if I multiply 5,000 by 3/4, guess what? I get what is left in the building, which is that same 3750, okay, as opposed to having to do 2 steps, okay? So if I use this new model of having 3/4, I can actually calculate my sequence, a sub 1 being 5,000, a sub 2 being 3750. Okay, now if I wanted to continue, I can continue multiplying by 3/4 to see that my third term would be 2812.5. Multiply again by 3/4 and see that on my 4th day I would have 2109.375. And I can continue this same pattern all the way down to my 10th day. Okay, now that's a lot of multiplication. And so that leads us to the second question. Is this sequence arithmetic, geometric, or neither? Well, we know it's not a result of addition or subtraction. okay? But the conversion of this subtracting from the total to multiplying by a reduced fraction tells me that we are actually going to have a geometric sequence, meaning I can use a sub n is equal to a1 times r to the n minus 1 to represent the situation. Okay, so I'm just going to erase some of this right here to help me do the next part. Okay, let's write a formula for the sequence and then use that to calculate it. So a sub n is equal to my initial term, 5,000, times my common ratio, which is 3/4 to the n minus 1. I want to find out how much is left on the 10th day. So I substitute in 10 for my n. Oops. And I get times 3/4 to the 9th power, approximately 375 cubic centimeters. So we've decreased from 5,000 cubic centimeters to 375. And we can use a formula to do this for this particular question. Okay? So let's take a look at another word problem and see, again, how these apply. So we have, when a ball bounces, the heights of the consecutive bounces form a geometric sequence. Okay, the height of the first bounce is 121 centimeters, and the height of the third bounce is 64 centimeters. To the nearest centimeter, what is the height of the fifth bounce? Now, again, if we were in class, you would see that this would be a gift of, right, my ball bouncing up and down. And so what makes it a geometric is that the height in which my ball bounces, right, follows a geometric sequence, meaning it's decreasing by the same amount every time until it hits the floor, okay? So because we see the word geometric sequence there, we know right away that a possibility is that we can be using our formula, a sub n is equal to a1 times my common ratio of n to n minus 1. What else do we know? The height of the first bounce is 121 centimeters, meaning a1 is 121 centimeters. The height of the third bounce is equal to 64 centimeters. To the nearest centimeter, what is the height of the fifth bounce? Okay, so here's the issue here. We don't have enough information to make a justification for what our common ratio is, right? We don't have two consecutive terms. But what we do have is a formula, okay? So if I plug in my formula using these two pieces of information, I should be able to calculate what my common ratio is to help me find my fifth term. So what do I mean? Well, a sub n is a sub 3. But we know a sub 3 is really equal to 64. So I can substitute 64 in for a sub n and 121 in for a sub 1. And this will leave me with my common ratio raised to the 3 minus 1 power. So 64, 121, r to the second power. Great. So now, even though we don't have our common ratio, we just have a quadratic here in which we can actually solve for the common ratio by isolating my square power and then taking the square root of both sides. Okay, now the square root of both sides in this case would be 8/11, making my common ratio 8/11. Now, technically, we need plus or minus, but because this is a real-world context, right, we don't need the minus. We know the bounce is not going to be negative. It's going to be represented by a positive value, okay? So that being said, we have our common ratio. We have our initial value. So my explicit formula for any term can be represented by 121 times 8/11 n to the negative first power. Okay, so now if I want my fifth term, all I have to do is substitute in 5 for my n value and plug this into my calculator. So that's 8/11, not 5/11, raised to the fourth. We get that A5 is approximately, since we're rounding to the nearest centimeter, 34 centimeters. Okay, so this is one way of calculating this, definitely 100%. However, some of you might have been looking at these two numbers and saying, wait a second, I have the first, I have the third. Maybe if I find my second term, okay, I can find my common ratio, right, by taking the A2 and dividing by A1. Because we know any common ratio can be found by taking, right, the A sub n term and basically dividing it by the term in front of us, okay? So if you were thinking along those lines, right, because we talked about that in the previous lesson, you might be thinking about some sort of mean to help us find this. So it's not going to be the same as the arithmetic mean where we find our average. Instead, we're going to talk about our geometric mean, which is finding the middle term of 3 consecutive terms in a geometric sequence. Now, it is calculated by the square root of x times y. Now, here's the thing. Because of the nature of these questions, this will help us calculate only the positive values. It will not necessarily help us calculate negative values. So we always need to keep in mind that there is a possibility that this value could be a positive number or a negative number. Okay, and that's because when we multiply by the same number twice, right, it can bring us both to positives. It could be done with both positive and negative numbers, right? So if I wanted to find the geometric mean or the missing term between these two values, something that I can do is take 2/5, multiply it by 8/45, and take the square root of it. Okay, so let's do that. That's square root of 16 over 5 times 45 is 225. Both of those are perfect squares. So 4 over 15, is the missing value. However, we don't know if that's a positive 4 over 15 or a negative 4 over 15, because if I multiply by the same number, right, we would get from positive to positive anyway. So we use a plus or minus to say, well, it is a possibility that it could be either a positive 4 over 15 or a negative 4 over 15. So now how can this help us with the next question? Okay, I mean the past question. Well, if we know that the geometric mean is found by taking A1, missing A2, A3, by taking A1 and multiplying it by A3, and this will give us our A2 value, we can then use that to help us to find our common ratio. So A1 is 121, A3 is 64. All right, so square root of 121 times 64 equals 88. Okay, so A1 is equal to 121, A2 is equal to 88, and A3 is equal to 64. Okay, so we can find our common ratio by taking 88 and dividing it over 121, or even taking 64 and dividing it by 88. In both cases, right, we get that our common ratio is 8 over 11, which is what we needed, right, to substitute in a sub 5. Okay, so whether you choose to solve it like an equation or you choose to use the geometric mean, in both cases, we are able to come up with a geometric explicit formula of 121 times 8 over 11, and we can substitute n equal to 5 to find the fifth bounce. Okay, so given that, here are your homework problems I ask you to try. Give it your best effort, and let me know if you have any questions.